Welcome to the presentation on microservices design in detail. In this session, we will explore the core concepts of microservices architecture, including service decomposition, API gateway, and inter-service communication. Let's dive in. Microservices architecture is a design pattern where applications are broken down into smaller, self-contained services. These services are designed to handle specific business functionalities and can be developed, deployed, and scaled independently. The key benefits of adopting microservices include scalability, independent deployments, and better fault isolation. Service decomposition involves breaking down a monolithic application into smaller services. To do this, we typically rely on domain-driven design, where we focus on the business domain to identify natural service boundaries. The challenge lies in determining the right granularity of each service, ensuring that each service is sufficiently independent yet cohesive in its functionality. To identify services, we use various techniques such as user stories, process mapping, and event storming. These methods help us analyze business processes and identify logical service boundaries. However, a major challenge is deciding the right level of granularity. Too small a service can create overhead, while too large a service might defeat the purpose of microservices. The API gateway acts as a single entry point for all client requests. It is responsible for routing requests to the appropriate microservice, managing authentication and authorization, and aggregating data from different services if necessary. Popular tools like Kong, AWS API Gateway, and Nginx can be used to manage and orchestrate API calls efficiently. Microservices rely on communication between services to function effectively. Synchronous communication can be achieved using REST APIs or gRPC, while asynchronous communication often uses message queues like RabbitMQ or Kafka. Event-driven systems enable services to react to events, making the architecture more responsive and scalable. In microservices, each service typically has its own database, ensuring that it is autonomous and scalable. We encounter different consistency models such as eventual consistency, which is often favored in distributed systems, and strong consistency when transactions require guarantees. Patterns like Saga help manage distributed transactions in microservices. Fault tolerance is crucial in a microservices architecture. The circuit breaker pattern, for example, helps prevent cascading failures by stopping requests to a failing service. Techniques like retries with exponential backoff can also help recover from transient failures, ensuring that the system remains resilient even in the face of errors. Security is a fundamental consideration in microservices. Each service must be securely authenticated and authorized using methods like OAuth2, JWT. Service-to-service communication can be secured using mutual TLS, while data encryption ensures that sensitive data is protected both in transit and at rest. CI/CD pipelines are essential for automating the deployment of microservices. Tools like Kubernetes and ECS allow for seamless scaling, ensuring that services can grow independently based on load. Techniques like blue-green deployments allow for safer updates, enabling rollbacks if necessary. To build and manage microservices, we use a variety of frameworks and tools. Spring Boot is a popular choice for Java-based microservices, while Micronaut is a lightweight alternative. Docker and Kubernetes provide the containerization and orchestration needed for scalable deployments, and monitoring tools like Prometheus and Grafana help ensure that the system runs smoothly. Let's look at a real-world example of microservices in action: an e-commerce platform. Here we could have a order service, inventory service, shipping service, and user service. Each service handles a distinct aspect of the platform, and they communicate with each other to provide a seamless customer experience. While microservices provide many benefits, they come with challenges. Service discovery is essential for locating services dynamically, and tools like Netflix, Eureka, or Consul are commonly used for this. Monitoring and logging become more complex, but tools like the ELK stack and Prometheus offer solutions. Additionally, ensuring data consistency and managing distributed transactions are crucial considerations that must be carefully designed. To summarize, microservices architecture enhances scalability, flexibility, and fault tolerance. Service decomposition is critical to success, and careful attention to API gateway management, inter-service communication, and data consistency will ensure a smooth operation. Security, resilience, and the right tools and frameworks play a vital role in the robustness of your microservices-based system. Thank you for your attention. If I would now like to open the floor for any questions or further discussions. Please feel free to ask anything related to the concepts we have covered today. Welcome to the presentation on serverless architecture design. Today we will explore the fundamentals of serverless architecture, focusing on popular cloud platforms, AWS Lambda, Azure Functions, and Google Cloud Functions. Let's dive in. Serverless architecture abstracts away server management, allowing developers to focus entirely on writing code. Instead of provisioning and maintaining servers, developers deploy functions that are automatically triggered by events. The cloud provider handles everything related to infrastructure, scaling, and availability. Serverless architecture offers several key benefits. First, scalability. It automatically scales based on demand. Second, cost efficiency. You only pay for the compute time your function uses, making it very cost efficient. Third, it reduces overhead by removing the need to manage servers. And finally, it accelerates time to market, allowing developers to focus on the business logic rather than infrastructure. Despite its advantages, serverless has some limitations. Cold starts introduce latency when functions are ideal. There's also the risk of vendor lock-ins, as you might become dependent on specific features of your cloud provider. Additionally, debugging and monitoring can be more complex due to the stateless nature of serverless systems. Let's start with AWS Lambda. It's Amazon serverless compute service that lets you run code in response to events. You can use it with languages such as Node.js, Python, Java, Go, and C Sharp. Lambda automatically scales and manages the underlying infrastructure for you. The core components of AWS Lambda include Lambda functions, which are executable units that respond to events. The API gateway helps in creating REST APIs to invoke Lambda functions. IAM rules manage the permissions, and the AWS SDK lets Lambda interact with other AWS services like DynamoDB or S3. Pricing for AWS Lambda is based on the number of requests your function receives and the execution time. You only pay for the time your function runs, making it a cost effective solution for many use cases. Now let's look at Azure Functions. This is Microsoft's serverless offering that allows you to execute code in response to events or HTTP requests. Like AWS Lambda, it supports multiple programming languages including C Sharp, Python, and JavaScript. Azure Functions consists of function apps, which are containers for your functions, bindings that connect your functions to external services like blob storage and Azure Event Grid, which can trigger functions based on various event sources. Azure Functions pricing is similar to AWS Lambda. You are charged based on the number of executions, the duration of function execution, and the allocated memory. It's designed to be cost efficient, especially for infrequent or sporadic workloads. Next, we have Google Cloud Functions, another serverless compute service that allows you to run your code in response to events from Google Cloud Services or HTTP requests. It supports multiple languages like Node.js, Python, and Go. Google Cloud Functions are built around function deployments that can be managed through the Cloud Console or CLI. Event sources like Cloud Publish subscription, publishing subscription, Firestore, or cloud storage can trigger these functions. Additionally, IAM and permissions help ensure that only authorized users and services can invoke these functions. Google Cloud Functions also uses a pay-as-you-go model. You are charged based on the number of invocations, execution time, and the amount of resources your function consumes. This makes it scalable and cost effective for a wide range of use cases. Serverless architecture is ideal for various use cases. You can build web applications by hosting backend functions. It's also great for real-time data processing, such as handling IoT data streams. Additionally, file processing workflows and microservices can be efficiently handled using serverless systems. When designing serverless systems, it's important to consider a few factors. Statelessness means that functions can't rely on in-memory data, so use external storage if necessary. Be mindful of cold starts that can affect latency and remember the execution time limits of serverless platforms. Finally, plan for scaling and the associated costs, especially when running large-scale applications. To design effective serverless architectures, here are some best practices. Keep your functions small and focused on a single task to ensure efficiency. Optimize for performance to minimize cost, cold starts, and always implement error handling for resilience. Use cloud native tools for logging and monitoring, and make sure your system is secure by leveraging IAM roles and validating inputs. In conclusion, serverless computing offers scalability, cost efficiency, and reduces infrastructure management. AWS Lambda, Azure Functions, and Google Cloud Functions each provide robust serverless solutions with unique features. By understanding the principles and best practices, you can design highly efficient and scalable systems using serverless architectures. That concludes the presentation. Thank you for your attention. If you have any questions or need further clarification, feel free to ask now. Welcome to this presentation on containerization and orchestration with Docker and Kubernetes, a critical aspect of advanced system design. In today's session, we will dive into the concepts, tools, and best practices for containerizing applications and orchestrating them with Kubernetes. Let's get started. Here's an overview of today's presentation. We will first explore the concept of containerization, followed by a detailed introduction to Docker. Then we will dive into Kubernetes, a powerful orchestration tool for managing containers. Finally, we will wrap up by discussing best practices for both Docker and Kubernetes. At the end, we will summarize the key takeaways. Let's begin with containerization. Containerization is a technology that allows you to package applications and their dependencies into a portable, isolated environment known as a container. Containers run on the host operating system, sharing the OS kernel but maintaining isolation for applications, which makes them lightweight and efficient. The benefits of containerization include portability across different environments, resource efficiency, scalability, and isolation, making it ideal for modern distributed applications. Docker is one of the most popular containerization platforms. It simplifies the process of creating, deploying, and managing containers. A Docker image is a snapshot of an application and its environment, which can be used to create Docker containers. Docker images are built using a Docker file which contains all the instructions for creating the image. Docker Hub is a repository where developers can share and pull Docker images for various applications. Here are some essential Docker commands. Docker build is used to create an image from a Docker file. Docker run starts a container from an image. Docker ps lists all running containers. Docker stop is used to stop a running container. Docker pull allows you to download images from a repository. These commands are fundamental for working with Docker in any development environment. Here is an example of a simple Docker file. We start with a base image, in this case the official Node.js image. Then we set the working directory, copy the application dependencies, and install them using npm. After that, we copy the rest of the application and expose port 3000 where the app will run. Finally, we specify the command to start the app using npm start. This is a basic example, but Docker files can get more complex depending on the application's requirement. Kubernetes is an open source platform designed for automating the deployment, scaling, and management of containerized applications. It manages a cluster of machines and runs containerized applications on them. Kubernetes is highly extensible and can support any kind of containerized application, making it the industry standard for container orchestration. Kubernetes follows a master-slave architecture with a master node controlling the cluster and multiple worker nodes running the containers. The master node contains essential components such as the API server, the scheduler, and the controller manager. Worker nodes run the kubelet and kube proxy components that ensure containers are running, and manage the networking between them. Here are a few important Kubernetes commands. kubectl get pods lists all the running pods in the cluster. kubectl create -f deployment.yaml creates Kubernetes resources like pods or services from a YAML file. kubectl scale deployment allows you to scale your application by adjusting the number of replicas. kubectl expose makes a pod available as a service so that it can be accessed externally. Here's an example of Kubernetes deployment YAML file. This YAML file defines a deployment for an app named MyApp, which runs 3 replicas of a containerized application. The deployment includes a container specification with a name and image and exposes port 8080 for communication. YAML is commonly used in Kubernetes for defining resources like pods, services, and deployments. Kubernetes provides powerful features for container orchestration, including scaling. It automatically adjusts the number of container replicas based on demands. Rolling updates. Kubernetes facilitates smooth updates by rolling out new versions of applications gradually. Self-healing. If a container fails, Kubernetes automatically restarts or replicates it to maintain the desired state. Service discovery and load balancing. Kubernetes help route traffic to the right containers, providing efficient communication and load balancing. Now let's look at some best practices for containerization. Keep containers lightweight, avoid unnecessary dependencies, making your containers smaller and faster to deploy. Use multi-stage builds. Separate the build and runtime environments to reduce image size. Organize with namespaces and labels. Simplify resource management in large-scale systems by categorizing containers efficiently. Automate with CI/CD. Implement continuous integration and continuous deployment pipelines to streamline the deployment process. To summarize, Docker and Kubernetes are powerful tools for managing modern distributed applications. Docker provides an easy way to create and manage containers, while Kubernetes helps orchestrate those containers at scale. By following best practices for containerization and orchestration, you can create efficient, scalable, and resilient applications. With these tools, your infrastructure will be well equipped to handle the demands of modern software development. That concludes our presentation on containerization and orchestration with Docker and Kubernetes. I hope you found the information helpful. Now let's open the floor for any questions. Feel free to ask anything about containerization, Docker, Kubernetes, or best practices. Welcome to the presentation on event-driven systems. Today we will explore the key concepts, design patterns, challenges, and best practices that drive the success of scalable and reactive architectures. Event-driven architecture or EDA is a design paradigm in which the application's flow is determined by events. In EDA, systems are designed around the occurrence of events such as user actions, sensor outputs, or system-generated messages. The main components of an event-driven system include event producers, consumers, and event channels. The architecture offers significant advantages like asynchronous processing and decoupling of components, enabling better scalability and flexibility. Events can be classified into two types, simple and complex. Simple events might include basic actions like user registration or a transaction. Complex events are combinations of simple events that trigger more intricate workflows, such as an order process involving multiple actions like payment, shipping, and customer notifications. The core components of event-driven systems include event producers, event consumers, event channels, and event source. Event producers generate events based on some actions or changes in state, while event consumers process those events. Event channels like message brokers handle the delivery of events, and event stores event for later use, such as auditing or event replay. In an event-driven system, events flow in a predictable pattern from the producer to the channel and finally to the consumer. For example, in an e-commerce system, a user making a purchase generates an event that is sent to the message queue. The event is then processed by the consumer, which could be the payment service that handles the transaction. There are several patterns for handling events in a system. In event notification, an event simply informs consumers that something has occurred, like an order being shipped. Event carried state transfer ensures that an event carries the necessary state for the consumer to process it. Event sourcing relies on events to build the state of the system, while CQRS separates the concerns of commands and queries for better scalability and performance. Despite their benefits, event-driven systems come with challenges. Event ordering is crucial for maintaining the integrity of the system and ensuring that events are delivered in the correct sequence is a key concern. Eventual consistency ensures that the system will eventually reach a consistent state, but this can cause temporary inconsistencies. Handling duplicate events and implementing failure management strategies like retries and dead letter queues are also important. There are several communication protocols used in event-driven systems. Message queues like RabbitMQ or AWS SQLs are commonly used for reliable message delivery. Publish subscribe models like Apache Kafka and Google PubSub are often employed for high throughput systems. Webhooks are lightweight HTTP based event notification systems, while an event pass facilitates communication between multiple services in distributed systems. Event driven systems are widely used in industries where real time data processing and decoupled systems are critical. Some of the common use cases include real-time analytics in IoT applications, e-commerce workflows like order processing, financial transaction processing, and microservices communication, where each service reacts to different events asynchronously. Several technologies and tools are commonly used to implement event-driven systems. Apache Kafka is a popular distributed streaming platform, and RabbitMQ is widely used for messaging queues. AWS SNS and Google Cloud PubSub offer cloud-based solutions for event-driven communication, while EventBridge provides a serverless event bus for building event-driven architectures. When designing event-driven systems, it's important to follow best practices. Defining clear event schemas ensures consistency in the way events are structured. Scalability can be achieved by ensuring that message brokers and event processing systems can handle high volumes of events. Failure handling mechanisms such as retries and dead letter queues ensure reliability, and partitioning events is essential for maintaining compatibility as system evolve. Let's consider an e-commerce system as a real-world case study. When a user places an order, several events are triggered. These events might include inventory checks, payment requests, and shipping preparations. By using an event-driven system, we decouple these processes, enabling independent scaling and improved fault tolerance. Each service, such as payment or inventory, reacts to the events it consumes. In summary, event-driven systems are powerful tools for building scalable and flexible architectures. They allow for the decoupling of components, which results in better maintainability and responsiveness. Key takeaways include understanding the components of EDA, recognizing the challenges it poses, and applying best practices to ensure your system can scale and recover from failures efficiently. Thank you for your attention. I would now like to open the floor for any questions. Feel free to ask about anything we have discussed today. Welcome to the presentation on designing for security and compliance. Today we will explore advanced concepts in system design, focusing on securing applications and meeting compliance standards. Let's dive in. In this session, we will cover a variety of topics. We will start with the fundamentals of security, moving on to the OWASP top 10 vulnerabilities, and explore key compliance standards. We will also discuss secure API design, security best practices, and privacy concerns, along with encryption and secure communication methods. Let's begin with the basics. The CIA triad: confidentiality, integrity, and availability. These are the core principles of any secure system. Confidentiality ensures that only authorized users can access data. Integrity guarantees that data hasn't been tampered with, and availability ensures the system is accessible when needed. Risk assessment and threat modeling are crucial to understanding potential vulnerabilities in your system. Next, we focus on the OWASP top 10, a widely recognized list of common security vulnerabilities. This includes injection attacks, where untrusted data is inserted into a query, and broken authentication, where weaknesses allow attackers to impersonate users. Sensitive data exposure and cross-site scripting (XSS) are also serious concerns, but they can be mitigated with proper encryption and input sanitization. Continuing with the OWASP top 10, we look at cross-site request forgery (CSRF), security misconfiguration, and broken access control. Implementing CSRF, protecting and maintaining secure configurations can prevent these threats. Insecure deserialization and using components with known vulnerabilities also pose risks, but regular updates and secure coding practices can help avoid them. Finally, insufficient logging and monitoring can make it hard to detect attacks, so consistent logging is essential. Now let's talk about compliance standards and regulations. GDPR mandates strict data protection policies and user consents. HIPAA governs the security of health-related data, while PCI DSS sets the standards for securing payment card information. FedRAMP ensures cloud security for US government systems. Compliance with these standards is crucial for maintaining trust and avoiding legal consequences. Designing secure APIs is fundamental to protecting your system. Using OAuth 2.0 or JWT for authentication ensures that only authorized users can access your resources. Rate limiting is essential to prevent brute force and DDoS attacks, while encrypting data during transmission and at rest keeps sensitive information safe. Input validation prevents vulnerabilities like SQL injection, and auditing logs are critical for tracking security events. To ensure your system remains secure, it's important to follow secure coding practices, regularly update libraries, and conduct code reviews. Patch management is critical to protect against vulnerabilities. Regular security testing, including penetration testing and vulnerability scanning, helps identify weaknesses. Lastly, an incident response plan is essential for efficient responding to any security breach. Designing for privacy means protecting users' personal data. Implement data minimization to only collect the necessary information. Anonymous, Anonymization and pseudonymization are useful techniques to protect user identities. User consent must be actively managed, and privacy considerations should be embedded in the design process, ensuring that systems comply with privacy laws and best practices. End-to-end encryption (E2EE) ensures that only the sender and receiver can read the data, protecting it from unauthorized access. Using TLS or SSL protocols for secure communication over the web is another key aspect of safeguarding data. These practices prevent man-in-the-middle attacks and ensure privacy during data transfer. To conclude, security and compliance are fundamental elements of system design. By following the OWASP guidelines and adhering to industry standards, you can create systems that are both secure and compliant. Always consider privacy, implement secure communication methods, and stay vigilant in managing threats. Thank you for joining this session. Now it's time to apply these concepts to your own designs. Hello and welcome. Today we will be diving into the concept of handling data consistency in distributed systems, part of our advanced topics in system design. In this presentation, I will be taking you through a series on at cutting edge system design principles. Let's get started. Here's what we will cover in today's presentation. First, we will introduce data consistency and discuss the challenges involved. Then we will explore the Cape theorem and various consistency models. We will also look at eventual consistency and its implementations. Later we will examine CQRS, event sourcing, and how consistency is balanced with latency. Finally, we will conclude with some real-world case studies and protocols that help maintain consistency in distributed systems. Data consistency refers to ensuring that data in a distributed system remains accurate, reliable, and synchronized across all nodes. Achieving consistency is crucial but challenging due to issues like data replication, network partitioning, and concurrent updates. In large-scale systems, consistency becomes even more critical for maintaining reliable operations. One of the foundational principles in distributed systems is the Cape theorem, which states that a system can only guarantee two out of three properties. consistency, availability, and partition tolerance. If a network partition occurs, the system must either maintain consistency or availability, but not both. This trade-off plays a major role in system design and needs to be carefully considered. To handle data consistency, we employ different consistency models. Strong consistency ensures that every read reflects the most recent write. Eventual consistency allows for temporary inconsistencies with the promise that data will converge eventually. Casual consistency maintains the relationship between updates, while read your writes consistency guarantees that a client always reads its own updates. Eventual consistency is a model where data replicas across a system will eventually synchronize, but for a period of time. There may be inconsistencies. This model favors availability and partition tolerance, allowing systems to continue functioning even if some replicas are out of sync. Examples of systems using eventual consistency include Amazon DynamoDB and Cassandra. CQRS or Command Query Responsibility Segregation splits the responsibilities for reading and writing data. This approach enhances performance and scalability. Event sourcing takes this further by storing all changes to data as immutable events, providing better scalability and ability to audit and track state changes over time. Both of these concepts work well in systems that need to scale while maintaining consistency. When designing distributed systems, there is often a trade-off between consistency and latency. Lower latency means transfer response times, but it might come at the cost of eventual consistency. On the other hand, prioritizing consistency can result in slower responses. Depending on the use case, systems must decide how to balance these factors. Achieving consistency in distributed systems is not without its challenge. Network partitions can cause nodes to lose connectivity, leading to data inconsistencies. Replication lag refers to the delay between updating a primary node and the time it takes for that to change to propagate to replicas. Additionally, concurrent updates can lead to race conditions where simultaneous data updates may conflict with each other. In databases, relational databases typically guarantee strong consistency using the ACID properties, while NoSQL databases often prioritize availability and partition tolerance, allowing for eventual consistency. Hybrid models like Google Spanner combine strong consistency with high availability, providing the best of two worlds for certain use cases. To maintain consistency, various consistency protocols are employed. Quorum-based replication ensures that a majority of nodes acknowledge a transaction before it's considered successful. Two-phase commit or 2PC ensures that all nodes in a transaction agree before committing changes. Consensus algorithms like Paxos and Raft are used to ensure that a group of nodes reaches agreement on the order of operations in distributed systems. Let's look at a case study on Amazon DynamoDB, which uses eventual consistency to ensure low latency reads and writes. DynamoDB prioritizes availability, making it a great choice for highly distributed systems where near instant access to data is required, but the latest data is not always necessary. Social media platforms like Facebook and Twitter are perfect examples of systems that use eventual consistency. When you update your status or post, it might take a while for that update to appear on every device or in every feed. The system focuses on quick updates and fast responses even if the data isn't immediately consistent across all replicas. In summary, handling data consistency in distributed systems requires balancing between consistency, availability, and partition tolerance, as described by the Cape theorem. Choosing the right consistency model using protocols like Paxos or Raft and understanding the trade-offs between latency and consistency are key to building efficient and reliable systems. Real-world examples like DynamoDB and social media illustrate the practical application of these concepts. Thank you for your attention. I would now like to open the floor to any questions or comments. Feel free to ask anything or share your thoughts on how these principles could be applied in your own systems. Hello and welcome to today's presentation on high-level design for real-time systems. We will explore various aspects for designing real-time systems, focusing on communication mechanisms, data processing, and the best practices needed for success. Let's start by understanding what real-time systems are. These are systems where the correctness of the system depends not just on the correctness of the operations, but also on the precise timing of those operations. There are two types: hard real-time, where meeting deadlines is critical, like airbag deployment systems, and soft real-time, where deadlines are important, but missing them does not result in catastrophic failure, like in video streaming. Real-time systems are widely used in fields like autonomous vehicles, IoT, gaming, and financial systems. Designing real-time systems comes with its own set of challenges. Key considerations include latency, which refers to the time taken for data to travel; throughput, which is the amount of data processed over time; fault tolerance, ensuring the system continues to operate even in case of failures; scalability, the ability to handle increased workloads; and concurrency, ensuring efficient execution of simultaneous tasks. Real-time communication is essential for the smooth functioning of such systems. WebSockets are a key technology here, allowing full duplex bidirectional communication with minimal latency, which is perfect for use cases like chat or live notifications. Stream processing, on the other hand, involves continuous processing of data streams as they arrive. Technologies like Apache Kafka and Flick play an important role in handling these continuous streams of data in real time, such as monitoring logs or sensor data. Let's dive deeper into stream processing. Event stream processing focuses on processing events as soon as they occur, allowing the system to respond almost immediately. Complex event processing, or CEP, goes a step further by identifying patterns in event streams, such as detecting fraud in financial transactions. Key tools for stream processing include Apache Kafka, Apache Flink, and Google Cloud PubSub, each offering scalable solutions for handling massive streams of real-time data. Real-time systems also require efficient data storage. In memory data In-memory data stores like Redis and Memcached are perfect for fast, read-heavy applications, while real-time databases like TimescaleDB and InfluxDB are optimized for time series data, which is common in real-time monitoring. Data sharding and replication are also crucial techniques to ensure scalability and high availability, allowing large-scale distributed systems to perform efficiently. Designing efficient real-time data processing pipelines is key. Message queues like RabbitMQ, Kafka, and ActiveMQ are commonly used to decouple services and ensure smooth data flow between components. In a publish subscribe model, multiple consumers can receive real-time updates from producers, while the point-to-point model guarantees that each message is delivered to a specific consumer. Real-time systems come with their own set of challenges. Latency and timelines are crucial, as even slight delays can affect the performance of the system. Concurrency and synchronization are also complex, as real-time systems often involve multi-threading. Additionally, quality of service, balancing performance, reliability, and availability must be carefully managed. Lastly, network constraints like instability or packet loss can also present difficulties in maintaining consistent real-time performance. Real-time systems have numerous real-world applications. For example, autonomous vehicles process sensor data in real time to make quick decisions. Online gaming platforms rely on low latency communication to ensure smooth interaction between players. Stock trading systems demand real time updates to process transactions and analyze the market. Lastly, IoT networks, which controls smart home devices and industrial systems, need real-time communication to ensure everything functions properly. There are many tools and technologies that help in building real-time systems. WebRTC is widely used for peer-to-peer communication, especially in real-time media exchange. Kubernetes help scale applications, while load balancer like Nginx and HAProxy ensure efficient traffic distribution, which is crucial when handling high volumes of real-time data. In summary, real-time systems require careful attention to latency, throughput, fault tolerance, and scalability. WebSockets and stream processing are the fundamental of real-time communication, while tools like Kafka, Redis, and Flink help manage data. Designing real-time systems requires balancing performance and reliability, all while overcoming challenges like network instability and concurrency issues. Real-time systems are transforming industries such as gaming, IoT, and finance, and their impact will continue to grow. That concludes the presentation. Thank you for your attention. I am happy to take any questions you may have.